and welcome back to our channel. Today we're continuing with our tutorial on programming and using CNC machines. At this point I have to say that what I wanted to tackle today is, in my opinion, the most challenging part of a lathe operator's job, which is creating grips and clamping systems. Normally, lathes hold the piece with 3 jaws mounted on a self-centering chuck. This is not always true. It is also possible to see real works of art that are customized gripping systems for pieces, for example in a cylindrical. Obviously this is not what we will be dealing with, but know that if you find yourself managing complex pieces, such as castings, die castings and so on, it is not mandatory to use clamps. For example, there are companies born to study special gripping systems that make masterpieces for gripping anything that can be put into rotation. We can't do that, so let's talk a bit about clamps. It's obvious that if I were to give you a course on clamps, I'd probably still be going in 2025 because it's impossible to cover all the alternatives. Just distinguishing between internal and external clamping would give us a ton of documentation to discuss, and even if I wanted to, I could never finish because the pieces you can find in machine shops are numerous and varied. So, what problems can we discuss in front of a whiteboard? Well, first of all, we can talk a bit about the difference between external and internal clamping. Why we need to go back to clamps and why we can't always use hardened clamps, and touch on some small issues of deformation and the distribution of forces on a rotating piece. So, when starting from a raw material, like a rolled piece, a forged part, or a cast piece, the first phase can be done by taking advantage of tempered clamps. So the operator does not have to return the clamps. And this is the advantage, the simplicity of the first phase. There are standard jaws, which I think all of you have seen at least once. They have serrated edges here, here, and here, and when viewed from above, they usually have a shape like this. These are self-locking, and all suppliers provide them as standard equipment. Alternatively, there are manufacturers of special clamps that make the classic clamp, which usually has an adjustment screw to grip only part of the serrated area. These are the clamps that, let's say, the only limitation they have might be the gripping diameter, and there's not much to do about it. You either have to use the standard ones or order them. Some even make their own, but that might not be the best thing to do because it can cost more than what's available on the market. However, when you're working on a piece like this, you do an initial phase, and let's say this is my turned area, and then I turn the piece. I can never turn it on clamps like these because otherwise my surface here would end up all pitted. Plus, when I go to turn this part here, I'll have a step, because if my clamp isn't turned on the self-centering, I won't have these two phases aligned with each other. Hence the need to turn the clamps. Another example could be a ring that is turned and drilled. So then for the second phase, I have my clamp to do the second phase, to have a grip here, I'll need to make clamps with an internal grip, for example, and position my ring like this to work on this area. There are many needs that can arise. First, let's examine in detail. The first rule for clamps. If I need to turn a clamp, this is the external part of the clamp that I will be turning, or the internal part, which is the part of the clamp that I will be turning. The first rule is always to create and establish a relief in the corner. So here for the external grip, and here for the internal grip. That's why you should always have in the machine or at hand an insert that allows you to make that relief. It's not the CNMG, but the rhombic 80 degrees. The right insert for turning clamps is either a triangular one with the right angle, or even better, a DNMG with the right angle. Alternatively, you can rough it out with a CNMG, but then finish with an insert at 35 to 55 degrees that allows for a relief. This is to facilitate the chip evacuation and ensure the stop. I hope I explained that well enough. Another rule is how precise the clamps I'm going to turn need to be, which depends on how I'm going to turn them. How do you turn clamps? If these are my clamps to turn, I recommend going back to my videos where I made a nice 3D explanation. Obviously, you can't just put the chuck in rotation. You need to firmly and securely secure the 3 clamps with a ring and close them. So, my advice for turning them is that when you buy new clamps, the distance between these points is not equidistant. You need to make it equidistant yourself. So my advice for turning is, which means you should pay very close attention to the details, specifically ensuring that all measurements are precise and accurate. This is crucial for achieving the desired outcome, which is to say, a perfectly turned clamp. Clamps are... This is the clamp seen from here. This is my central ring. First, do a rough turning at any diameter. Then, remove this solid ring and put on a ring with a hole large enough to allow a drill to access this area, and then put on the correctly sized ring to turn the clamps. 3 steps to have the clamps turned perfectly. If someone is watching me and says to use a caliper, go ahead and use the caliper because it's great for roughly turning clamps. But if I need precision, I have to do 3 steps: a rough cut, a ring, a finishing cut, and another rough cut. Okay. Turning in steps. Another rule for turning clamps. When I'm turning clamps, in external grip, let's say I need to achieve a diameter of 100, my clamps should be turned to 100 minus. I always recommend, generally speaking, undersizing the clamps by approximately 0.05, so if I'm aiming for a diameter of 100, I'll try to turn it to a diameter of 100 or so as a rule of thumb in practice. 22 or times 90 90, 95. How do I measure it? I either trust my tool, or I make some spaces, or use a 3-point micrometer for precision. But that measurement has to be known for a reason, and I'll explain why. If this is my clamp, and I've turned it too large, my piece, which is smaller, will only touch at 1 point. If I've turned it too small, it will touch at 2 points. So with 3 clamps, it will touch at 6 points, giving me a better distribution of the forces at play. Mathematically, there's no way to turn the pieces to the exact size of our piece. It's impossible. Zero error doesn't exist. So make sure to allow for some error on the better side. So for external turning, you turn down by 5/100. Obviously, when you have internal grip, it changes. You turn up by 5/100. This is your internal diameter, and this is your piece. If the piece has a diameter, a larger one will touch. A piece, if you think of a smaller diameter, in 1 point it will touch 2 points. This is very difficult to do on the blackboard. I'm trying to give you a lot of information, one after the other. Now, when turning clamps becomes tricky, it gets complicated, especially when I have to make a particularly thin ring. It's easy to understand that if I press on 3 points of a thin ring, just think about a diameter of 100 with a hole of 90 and a self-centering chuck that pushes down about 10 at the base. I turn the inside to 90. And when I go to measure it, my inside will be trilobate. Okay, this is a bit of a loser trilobate, but obviously I will go back to the machine, measure my nice 90 diameter with the closed chuck, and when I take it out of the self-centering chuck, it won't fit, because if I measure it, I will always find 90. But if I measure it in 3D with 12 contact points, I might find, for example, 89.2 or 90.2. So this piece will be squished. Here come the little details. If I have this famous ring with a diameter of 100 for 90, instead of comparing wide clamps of 40, I buy wide clamps of 80. Okay, these are my 3 clamps that are 80 millimeter wide, and I will do a turning as I explained in 3 steps. Then I will go back to the diameter. I said I need to reach 99.95. The finished size is 100, but I'm not satisfied with that, not at all. Let's say I have powered tools, and I'm lucky. Otherwise, I would have to use a flexible tool or a Bosch. I will do a pre-turning at 99 of this diameter. Then we said we took these are my 3 clamps that are 80 millimeter wide, and I'm going to do a turning as I explained in 3 steps. Then I'll go back to the diameter. I said I need to reach 99.95. The finished size is 100, but I'm not satisfied with that, not at all. Let's say I have powered tools and I'm lucky. Otherwise, I would have to use a flexible tool or a Bosch. I'm going to do a pre-turning at 99 of this diameter. And then we said we took 60 millimeter clamps. I'm going to grab a candle cutter and I'm going to make 3 notches of 15 millimeter in this area. Then I go and finish my turning here, 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 and here at 99 and 95. What happens? What happens is that I no longer have 3 contact points, but I have 6, which essentially and effectively reduces by half the force of my self-centering chuck. By distributing the force of my self-centering chuck over 6 points instead of 3, I prevent as much as possible trilobing and still have a very dependable and trustworthy grip on my workpiece ensuring it won't move during the turning phase. Okay, I hope I was understandable and clear. So, it's very crucial and important when preparing the clamps to distribute the forces. When the piece comes out well, you should always take note of the closing pressure of the self-centering chuck in the program. If it works well once, it should work well every time, except under certain special conditions. Remember one more thing regarding rings, particularly and especially if you're working with mechanical tubes. No matter how careful you are, if you have a mechanical tube and small rings to make, and you can't get them to be round no matter how well you turn them, they always end up being oval in shape rather than tri-lobed. This means that the hole size isn't uniform and consistent along its diameter. This can particularly and especially happen with iron tubes, and you may be compelled or forced to do stress relief treatments. Okay, there's no way to solve this issue other than relieving the material. I really wanted to make this tutorial mainly because I wanted to highlight and emphasize that you haven't just learned to program and think, now I'm a turner. That's not true. A turner becomes one when they know how to handle and manage the deformations of the workpiece and the things I've talked about. If you haven't understood them, don't worry, because I can't transfer that knowledge through video. It's too difficult. In conclusion, as I have mentioned before, it's a complex skill that requires practice and experience. To succeed as a turner, be humble and learn from experts. Manage technical issues like chip handling and vibrations. Experience varies by company. Build industry connections. See you in the next video on programming. Thank you. And moving. An X and a Z isn't being a turner. It's being a programmer. Being a turner means managing this type of problems like the ones from the previous video. So dealing with squaring machines means knowing how to handle chips and eliminate vibrations. I've thought about making a video on vibrations, but honestly, it's not really possible with just a video, because there are many complex issues, but you need to put in some study and give yourself a few years to gain experience, which varies from company to company. I, as a consultant, often get called to solve problems I'm not familiar with, for which I have to gather information from other companies, and that's the strength of a true turner, not necessarily knowing a problem, but being able to analyze and manage it from a technical standpoint, and sometimes with a bit of humility, calling a friend who has been working with super alloys for ages, or going to a pipe company and asking for help. Not everyone is willing to help, so you also need to build a network of friendships in the industry. I hope I've been helpful this time too, and I look forward to seeing you in the next video, where we might start looking at some programming again. Thank you very much. Bye. Bye. Thank you much. Bye.